We present an efficient post-processing approach for particle-based methods to locally improve the behavior of splashes on coarse liquids. Even today, pushing the simulation resolution high enough to generate these splash details is still computationally expensive and can be a tedious process for VFX artists. Splash details are automatically generated at locations where they are dissipated or non-existent in low-resolution liquids. Our approach generates detailed and customizable splashes using solely low-resolution input liquids. Our post-processing splash modeling approach supports both liquid-liquid and liquid-solid interactions. We first compute a volume over time from the intersections between an identified upsampling volume and colliding volumes. This volume we call splash volume is computed using exclusively the input animation of the low-resolution liquid. The union of each volume computed at every frame generates the splash volume. Solely the intersection between this volume and the low-resolution volume is kept as the final splash volume. Lastly, we discretize and expand the splash volume as cells for further upsampling process. We upsample particles inside selected cells of the splash volume. The upsampled particles evolve between three different states. Bulk is the initial state of the upsampled particles. The particles are flagged as ballistic as soon as they leave the low-resolution liquid interface. The impact state is triggered when the ballistic particle intersects back with the coarse liquid interface. A fourth type of particle is introduced to apply artificial forces according to another user-defined parameter. These so-called tracers are seated among ballistic particles to control surface tension within the generated splashes. Since these tracers are basically ballistics, their trajectories can be easily edited manually or procedurally. As shown in this close-up, we can interactively modify the appearance of a ground splash simply by adjusting the position and influence radius of the tracers. Tracer particles allow us to generate realistic and tailored splashes. One of the biggest advantages of our approach is its flexibility. Once the pre-computation steps are performed, our approach can easily generate multiple variants of the same upsample liquid at low cost. Finally, we introduce a novel linear wave model to infer displacement to input low-resolution particles. We distribute surface points uniformly over a low-resolution liquid surface at the first frame of the animation. Our wave model generates detailed swirls with very few surface points as opposed to the presented state-of-the-art method. Our approach has been used in several scenarios to demonstrate its practical flexibility. The speedboat ride scenario is a very good example in which we push the limits of our method. It would be reasonable to think that our approach could be even more costly than a traditional particle-based simulation method if the resulting splash volume was generated over the whole domain. Even though generating the splash volume has proven to be more expensive in this case, our computation times are still lower than the high-resolution simulation. A classic example in which we demonstrate the efficiency of our approach to generate ground splashes in low-resolution liquids. We also used our approach in comparison with high-resolution liquids simulated with millions of particles. Similarly to the fractal fruits example, this scenario shows how we can improve the splash details during solid-liquid interactions. Our approach was also used in a more dynamic scenario. In this scenario, our splash volume is upsampled over time to improve the particle distribution before the splash occurs. As shown in this side-by-side comparison, our approach successfully recreates highly detailed splashes comparable to the high-resolution reference. We compared our work with the state-of-the-art methods as well. As presented, our approach generates highly detailed and parameterizable splashes at computation times below procedural methods. Finally, our approach was successfully integrated using a hybrid DFSPH method. In this example, upsampled particles were added within the narrow band of the SPH particles.